Josiah Jasper. Yes. Sorry.
Last name? Gal.
Gal.
Thank you.
Okay. I'm going to go over the exam today. Before I do that in a second, maybe, I'm going to talk about differentiating power series today, which is a great thing about them. It means that power series act a lot like polynomials. So last time, so we have a power series, f of z equals, I'll write it like this, a naught plus the sum is n goes from 1 to infinity, a n z minus z naught to the n. And that has a radius of convergence, let's call it r sub f. And the fact is, f prime of z, when you differentiate that thing above, treat it like a polynomial, the derivative of the constant term would be 0. And then this would be the sum as n goes from 1 to infinity, n, of n a n z minus z naught to the n minus 1. Which when you, if I do a change of variables, let's see, it's the radius of convergence of this power series, it will call r of f prime. And when I mess around and write this, see, I'm going to do like a change of variables. Curly n equals square n minus 1. That would be the sum. I want to have the powers be the n. Okay. And then little n would be curly n plus 1. And I'd have a sub curly n plus 1 here. So that would be writing it in terms of the power n. And as n, little n, square n, goes from 1 to infinity, curly n goes from 0 to infinity. Okay. And the easy fact, so we know that f prime is analytic. F prime is analytic, where f is. And so that makes it very easy, since we know that the radius of convergence is bigger than or equal to the biggest radius where the thing is analytic. That fell out from the Cauchy integral formula. And so that makes it very easy to know that the radius of convergence of f prime is greater than or equal to the radius of convergence of f of the power series. And I'm also going to write this f prime as, I don't know that these coefficients are what I'm telling you they are there. I'll write this as the sum as n goes from 0 to infinity of bn, z minus z naught to the n. I'm going to show you that those bn's are given by the formula that you get by differentiating term by term. Okay, so we know that the radius of convergence of f prime is bigger than or equal to r sub f. And last time I showed you that if it was strictly bigger, then you'd take it. So last time, I showed if the radius of convergence was bigger, strictly bigger, then you could take an antiderivative of that function. So that power series would converge to something, and I called it fancy f. And then you could take an antiderivative of fancy f and see that the power series for little f converges on the same, at least that bigger disk, and that's a contradiction. So the trick was take an antiderivative did I call it capital F? I got too many F's here. Take antiderivative f, and you see that capital F equals little f on the smaller disk, on the RF disk. And this shows that the radius of convergence for the series for little f is bigger than it is. Get a bigger ROC for my little f, and that's a contradiction. So I did that last time carefully. It's kind of a weird thing to think about. So we conclude that the radius of convergence is equal to f. I mean, the radius of convergence of f prime is the same as the radius of convergence of f. And so the last thing I need to do today, the final step, to see that you can differentiate power series term by term, that Bn thing is a Taylor coefficient. So that would be f prime nth derivative at z naught divided by n factorial. And of course, the f prime nth derivative is the n plus first derivative at x naught. And that looks weird. The n factorial, I kind of wish there was an n plus 1 factorial on the bottom. And so I'm going to give that to myself by multiplying by n plus 1 on the top and the bottom. And then voila, I see that the b sub n is equal to n plus 1 times the n plus first derivative of z naught divided by n plus 1 factorial. And that's the an. That's an plus 1. And so, and that's exactly what this is my curly n formula. This is what I expected them to be in the curly n formula. So n plus 1 times an plus 1. And if you go back and look at my curly n formula, that's what you get. There it is. That's what you get for those Taylor coefficients if you differentiate term by term. So that completes the argument. Surprisingly sophisticated argument. Another way to do this thing is often done in books is you just differentiate it term by term and then sort of start from scratch and find the radius of convergence of that. You can also use Hadamard's formula to do that. Anyway, it's more work. This just uses simple facts we know. That's why I always do it this way. So that's a big check. You can think of replacing n by curly n and see the formula above. Well, I'm going to continue and give you a famous example. in a minute. So, any questions about that? This is a fun example. Everybody's heard of the Fibonacci numbers. Fibonacci numbers. Let's see, A naught. Let's make A naught be 1. And let's A1 be 1. And then after that, the next one, AN, is the AN minus 1 plus AN minus 2. That starts at n equal 2, for n bigger than or equal to 2. So you start with 1, 1, add the previous 2 up and get 2. Add the previous 2 up and get 3. Add the previous 2 up and get 5. Next one is 8, etc. Those are famous numbers, and they appear in nature all over the place. Okay, and that's the thing we're going to think about. We're going to think about the power series you get by making the Fibonacci numbers the coefficients. So I don't know anything about it yet. I don't know if it converges. So we'll stick in the Fibonacci numbers as coefficients. This kind of thing is actually done in practice. It's sometimes this is called a generating function when you're doing combinatorial things. And it turns out to be useful in solving combinatorial problems. Generating function. So there's going to be an analytic function associated with this combinatorial problem. It leads to all kinds of interesting things. In a minute, I'm going to show you that the radius of convergence for this thing is the golden ratio. Radius of convergence is the famous golden ratio. What is it going to be? It's going to be square root of 5 minus 1 over 2. Not factorial, but exclamation point. I'll do that in a second. I thought I'd go over the exam first. Right? Any questions about anything? Let's see. So I didn't bring a copy of the exam. I should be able to memorize it, have it memorized. So let's see. The first problem was to show that if a function u, a harmonic function u, on a domain has, if you have two harmonic conjugates, then two harmonic conjugates, then the harmonic conjugates have to differ by a constant. What's your last name?
Walsh.
What?
Walsh. W-A.
Okay, so two harmonic conjugates of the same function differ by a constant. And of course, the Cauchy-Riemann equations are key here. If you have two of them, then you write the Cauchy-Riemann equations and see that the partial derivatives of those two functions, call them v1 and v2, would be the same. Okay, so that a part of the problem was to write down the Cauchy-Riemann equations correctly and deduce that fact. So that means the gradient of v1 is the same as the gradient of v2 on the domain. And so if you let v be v1 minus v2, the gradient of that v would be identically 0. And we showed that if the gradient of a function is identically 0 on a domain, then it's constant. People could have just quoted that fact. Instead, a lot of people tried to use the algorithm I showed you that worked on a disk. And it was important when I did that argument that the partial with respect to x along horizontal lines, it meant on horizontal lines, if dv by dx is identically 0, v would be constant on that horizontal line. Okay, that works on a disk when the horizontal line is in the domain. If you don't have a disk, then you got to think about something else. And we have thought about that. That's exactly what we did. So remember what we did when we proved this fact. We would have a domain. It could have holes. Horizontal lines could be going in and out. It could be weird shaped. Okay. So this is a bad domain. The horizontal lines would be going in and out, and you couldn't use that argument. And so what we did in this case is I fixed at point A and let Z slide around, and then I took a curve that started at A and went to Z and integrated along that. And the fact that, and here's what we did, we went zigging and zagging along that curve. So I guess I want to make this a simpler thing. Let me make my Z here. There's a Z. And I'll make my curve going from A to Z. Remember what we did? We went horizontal, vertical, horizontal, vertical. And then if it's those partial derivatives are 0 in the horizontal direction and the vertical direction, it remains constant. And so we zigged and zagged along that curve and see that it'd be constant. That it'd have the same value at Z that it has at A. That was the key to that argument. That's how we did that. But you could just quote that as a fact. If the gradient of V is equal to 0 on a domain, then V is constant. Messing that up was worth 5 points. Questions about that? Yeah.
The key thing about this is that it specifies only constant on a specific domain.
Well, if you did that, if you were trying to use the PDE approach to solving it like we did on a disk, when the thing was polynomials, when it was fairly straightforward, you would show that the thing is constant on a disk. And this argument involving domains with a curve and using connectivity was important. You could turn that into an argument using connectivity, but if you know it's constant on disks, it would have to be the same constant as you drag along that curve. Anyway, that was a minor issue. The next problem was about calculating an integral. And let's see, we're going from 1 plus I to minus I. So in the plane, 1 plus I is over here, and minus I is over here. And what are we missing? Are we missing the real line?
Positive reals.
The positive reals. So we're not allowed to go through 0 or the positive reals. And so a typical curve that does that, it could be really weird. It could go down and get real close to the positive real line, and it could curl around and do this. Then it could go back and get close over here and then end up like that. So we've got to come up with a way that allows for that weird of a curve. And so the key is having an antiderivative. And so that would be the complex log function. And to make it analytic where that curve is going, we would have to take the branch where the branch cut is the positive real axis. Okay, that's what I call log 0. That would mean the angle would go from 0 to 2 pi. So as you go along this direction, the angle would be 0, and after you go all the way around, the angle would be going to 2 pi on this side. Which means right here at 1 plus I, the angle is pi over 4. So I'm going 0 to pi over 4. I keep going around, and here the angle would be 3 pi over 2. Okay, using that branch of log, so it would be, the real part's always the natural log of the modulus of z, no matter which branch you pick, but it's the choice of the angle that determines the branch, and the angle is an argument of z, and we're taking the argument that's between 0 and 2 pi. Okay, so that was critical to define that branch and to use it properly. And so let's see, this would be the log, that branch of the log, at the end point minus the start point. At the end point, it's log of the modulus of minus I, which of course is 0, plus I 3 pi over 2. And then at the other end, it's the modulus of 1 plus I is square root of 2. So it would be minus the log of square root of 2 plus I times pi over 4. And so that's how that's done. Questions about that part? This one was a homework problem, so I figure it was kind of a giveaway. If f is entire and the real part of f is bounded by anything, in this case I made it bounded by 0, so I'm going to write f as u plus iv. And f is entire. So e to the f would also be entire. The hint was to look at e to the f. And you have to realize that e to the f would be e to the u plus iv, which is e to the u times e to the iv. And the modulus of e to the I anything real is 1, because that'd be cosine v plus I sine v has length cosine squared plus sine squared equal 1. And the modulus of e to the u is, since it's real and positive, is just e to the u. And so we see that the modulus of e to the f is equal to e to the u, and u is less than 0, and the exponential function is increasing. So e to the u is less than e to the 0, which is 1. And so now we have that the modulus of e to the f is bounded. In fact, it's bounded by 1. So Liouville says that a bounded entire function is constant. So we've deduced that e to the f has to be constant. And many people said, okay, well, we know that means that, let's say e to the f is c, then that means that f is the log of c. You can't do that in the complex case because the log is a multi-valued function. That works great in the real case. So there's a final hitch in this problem that you got to show that e to the f being constant when f is analytic would force f to be constant. I think I did this in class once. So f is constant. Therefore, e to the f is what? Oh, because, I'm sorry. We know that e to the f is constant. So therefore, the modulus of e to the f would be e to the u. That's a real constant. Okay, that's the formula above. The modulus of e to the f is e to the u. And we know the modulus, we know that e to the f is constant. So that modulus is constant. Call it c. Of course, it's bigger than 0 because e to the u is always non-zero, bigger than 0. So that means we can take the log of that equation and see that u is the real natural log of c. Okay. And v is a harmonic conjugate for u, so the Cauchy-Riemann equations would show you that the gradient of v is 0. And so once again, gradient v being 0 means that v must be constant on the c, which is a domain. So that was a 5-point part of the problem to do that properly. Questions about that? Okay, the last problem is the one about using the Cauchy integral formula to calculate an integral. Part A, well, the important thing to realize is that you can factor the denominator into z squared plus 1 is z minus I times z plus I. And so this looks like the Cauchy integral formula. The problem is there's 2 points. And I've shown you this trick where if you cut up the domain into 2 pieces, you can do the Cauchy-Riemann equation, the Cauchy integral formula on both of them and add them up, and the cuts cancel. The cut cancels. So you'll notice I have 2 counterclockwise simple closed curves there. Let's call it gamma top and gamma bottom. When I add them up, I get the integral around that circle of radius 2. And that circle contains both plus and minus I. So the key is if on the top, if I look at half of the thing being e to the iz over z plus I, that's analytic on the top. And if I look at the other half being e to the I over z minus I, that's analytic on the bottom. So this would be the Cauchy integral formula for those 2 functions on the top and the bottom. And you notice it's just the Cauchy integral except the 2 pi I isn't there. So I have to multiply by 2 pi I. And so you get 2 pi I times f of I on the top half and 2 pi I times g of minus I on the bottom half. Most people got that right. Another way to do it is partial fractions. I'll mention that at the bottom here in a second. Questions about part A? I think that's the easiest way to do it. Yeah.
How did you get the coefficients on f and g? Like how do you know that f is equal to that e to the z over z plus I?
Let's see. So that, for example, the gamma top here, that's e to the iz over z plus I over z minus I dz. And let's so I'm calling this thing here is my f of z, which is analytic in the top half. And if I put a 2 pi I here, no, if I put a 1 over 2 pi I, then this would be equal to f of I. That's the Cauchy integral formula. You see that? And you can do the same thing at the bottom, except then the function would be the g. Okay. That's the most easiest way to do that thing. In the second one, I'm going clockwise. That means instead of being the usual Cauchy integral formula, there'd be a minus sign in it. And if I take the circle of radius 1 about I, that, let's see, what would that look like? We've got a circle of radius 2. We've got plus I. We've got 0. And we've got minus I. And I take a circle of radius 1. Then there's no zeros there's no other 0 in there, or singular spot. And so that's just the Cauchy integral formula. using the little f function. So it's the same formula as above. It's just like the gamma top curve. And that's half the thing minus, you do it, get minus pi over e. And then the last one is the circle of radius 1/2, which would be this little thing here, and it's analytic inside that one. And so it's 0 by Cauchy's theorem. Since it's analytic, the integral around a closed contour like that would be 0 if it's analytic inside and on. And I mentioned you could use partial fractions to make it an even easier problem. Reduce it to the straightforward Cauchy integral formula. Some people forgot how to do partial fractions and got the coefficients a and b wrong. You multiply through by the denominator on the left and then do linear algebra, equating coefficients. Questions about the exam? Okay, well, I'll post those solutions on the home page after class. Okay, I want to go back to this Fibonacci problem. It's kind of fun. So, we don't know that this power series converges at all. So, let's assume for the moment. So I'm thinking out loud now. Let's assume for a moment that it does have a radius of convergence, that the series has radius of convergence r bigger than 0. We don't know that it does. Well, then we know we can differentiate term by term. Okay, so we got this f of z equals a naught plus a1z plus a2z squared plus blah, blah, blah. Let's say plus a sub n z to the n. Okay, let's think of f prime of z equals a naught I don't have to I thought this was an example of differentiating power series, but it's not. I differentiate and that would give me n times an. But I have this recurrence formula for the Fibonacci numbers. And so I'm thinking out loud now. Z times f of z would be a naught times z plus a1 times z squared plus etc. Let's see, I'd have a n minus 1 z to the n minus 1 z to the n plus a n z to the n plus 1 plus etc. And if I do that again, I'd get z squared f of z. If it has a power radius of convergence positive, I can do this. The next one would be a naught z squared plus a1z cubed, etc. Let's see, this one would be a n minus 2 z to the n plus a n minus 1 z to the n plus 1 plus etc. And I have a recurrence formula. A_n is equal to a_n minus 1 plus a_n minus 2. So the aha here is I'm looking at this column right here. AN is the sum of the previous two. And so starting at the n equal 2 spot, so if I write here, I'm going to take f of z minus z times f of z minus z squared times f of z. Is that a, let's think if that's 0. It's not quite 0. That first column gives me an a naught, which is annoying. The second column gives me a1 minus a naught times z. But after that, a2 is equal to a1 plus a naught, by definition. So at that point, it's 0, and it's each one of those cancels out, and I get 0, 0, 0, 0 from that point on. So plus a big fat 0, plus 0, plus 0, plus forever. And so if the thing does have a positive radius of convergence, let's see, a naught is a 1, and a1 is a 1, and a naught is a 1, so that's a 0. So I get if r is greater than 0, then f of z has to be equal to, I can solve this for 1 over 1 minus z squared. And now I have to do something mathematical. Right now I've just been playing games, imagining what the possibilities are. So the breakthrough moment is, I've been using that little f, but I'm going to let capital F of z be equal to 1 over 1 minus z squared. Let's see, where are the zeros of that thing? Capital F it's analytic near the origin. In fact, where is it analytic? Let's find the zeros of that quadratic thing. The zeros are, let's see, the quadratic formula is minus b, which would be minus 1 plus or minus the square root of b squared would be minus 1 squared minus 4ac. A is minus 1, c is 1. So it would be minus a minus 1. So it would be minus 4 times minus 1 times 1. What did I say the answer was going to be? Over 2a. So that would be 2 times minus 1. So what the heck am I getting? So that's 1 plus or minus the square root of 5 over minus 2. So that's square root of 5 plus or minus 1 over 2. Where do those fall on the complex plane?
How do you get plus or minus 1?
What? Minus b?
Like, isn't it still like negative 1 on a plus or minus 5?
Let's see. 1 plus 5. Well, I've got a minus 2 on the bottom, so I put the minus to the top. That's why it's flipped.
Shouldn't 1 just be minus? Why is there a plus on the 1?
A plus 1?
If it's negative 5, then that would be... If it's
I wrote the stupid quadratic thing backwards, so it's minus x squared minus z plus 1. So the a is minus 1, the b is minus 1, and the c is plus 1. So I think I have it right.
Right, but the question is if we have 1 plus the square root of 5, 1 plus the square root of 5 divided by negative 2 would have negative 5 and negative 1, which is impossible with the second equation to write down. Take the final one.
What? I'm taking the negative of the whole thing.
Right, but 1 plus 5, right? If it was a plus, is negative 1 minus 5.
Oh, I see. So it should be... So what am I trying to say here? It's minus... Thank you. That's pretty dopey of me. Yeah, so if I take that, I would get minus 1, still plus or minus the square root of 5. Okay, so where are those falling on in the complex numbers? Minus 1 minus the square root of 5 over 2 is, I'm saying, is a bigger negative number. So minus 1 minus the square root of 5 over 2 is way over there someplace. Whereas minus 1 plus the square root of 5 is closer to the origin. This would be minus 1 plus the square root of 5 over 2. That's going to turn out to be the radius of convergence. So that f is analytic on the plane minus those 2 points where it has a singularity. And so, in fact, we can see that the radius of convergence is... the biggest disk you can make it analytic on is this. And that's radius equals square root of 5 minus 1 over 2. That's the biggest disk where the thing would be analytic about the origin. And since it has a singularity there, that is the radius of convergence. So, so the radius of convergence of the power series for f is this golden ratio, square root of 5 minus 1 over 2. Okay, and now the aha moment is that I know that capital F of z is 1 minus z squared. What am I saying? Let's see, what do I know? I know that f of z times 1 minus z squared is equal to 1. And now if I were to write out the power series, this is going to be the sum as n goes from 0 to infinity, bn z to the n, times 1 minus z squared equals 1. Write that out. You see that the b's satisfy the Fibonacci recursion formula. The b ends satisfy the Fibonacci recursion formula. And they are the Fibonacci numbers, equal to the ANs. So we're done. That's how you do it. Now we know it does have a positive radius of convergence. Like we know what it is. And so the Fibonacci numbers give you a power series with the golden ratio being the radius of convergence. So this is how we see. We have to write it out and do it, but we see that That's how you do that. Questions about that? That's a fun thing to do with power series. Yeah.
The reason why we're able to say since never mind.
So that thing I did playing around with assuming it had a positive radius of convergence allowed me to see what that function would be in that case. And once you know what that function would be, then you can start with that function and forget how you got it. and the last step is to see that, that function does have the Fibonacci numbers as coefficients in the power series. By the way, this uses a key fact that the power series coefficients are uniquely given by the Taylor's formula. Key fact. Power series coefficients are unique they are given by the Taylor coefficients. Taylor's formula. That's a fact we know. So if two power series converge to the same function, two analytic functions, f of z equals summation an z minus c naught to the n, and a g of z equal to bn if f equals g on a little disk, can be really small, then of course all those coefficients have to be equal. This is a standard way to solve differential equations. You put the functions in the differential equation, write them as power series, combine them, and then if that's going to be a solution, it's 0, and then you realize all those coefficients have to be 0, and then you can use the recursion formula to figure out what all the coefficients are. I'll do an example like that at some point. Then all the ANs equal to BNs. Well, Friday I'm going to give you some homework hints, and I want to show you that section on Hadamard's formula. So, and if you can't be here on Friday, of course you can always catch the video in the aftermath. Any last minute questions about anything? Yeah.
So if like the radius of convergence of our series had been 0, then would something have like broken when we were trying to recompare our new
Well, then my inspiration wouldn't have given me anything. I got a formula, and it'd say that if that formula gave me a useless thing, I'd be sunk. So it just got me started to guess. I'm going to guess that the function actually has to be something very specific. And so, in fact, that's a common thing to do in this thing. You get a formula for the generating function, and then you deduce things about those coefficients, combinatorial numbers. It's a classic technique. Getting the formula is usually the hard part. Okay, question?
You keep saying that the radius of convergence with Fibonacci questions is the golden ratio, but isn't square root of 5 minus 1 over 2 not the golden ratio?
Isn't it? It's
Because
what is the
less than
golden?
1.